This morning, I'll update you on a project that our group is working on, led by Erin Bethell, which explores, which explores more about the preservation of rift in the Abitibi and their associations with VMS deposits. Erin was kind enough to send me a photo, looking very sad, having to go on this research vessel on Sunday and having to avoid the Canadian winter, the rest of the Canadian winter. So she sends her apologies, but is happy for me to present some of the preliminary results she has. So we're going to zoom out completely from Sarah's zircons all the way to the sub-province scale. So sub-province data sets, sub-province scales, sub-province processes. So the Superior Craton hosts about 4/5 of the world's Archean VMS tonnage, and the vast majority of this is in the Abitibi sub-province. On the plot on the right, you can see that the VMS tonnage versus area of volcanic rocks, in addition to some of the other superior sub-provinces, and it clearly shows that the Abitibi exhibits significantly higher VMS endowment than many of the other sub-provinces, even allowing for changes to these values from yet as undiscovered deposits. So our real question, one of these questions, is what conditions made this area so favorable for VMS deposit formation? If we focus in on the Abitibi, we can look at the distribution of VMS deposits. We know that they're they're not equally distributed, either spatially or temporally. Here we have on the map on the right the Methyl Earth lithological compilation by Taus and Harold, with the VMS locations overlain on top of those. And you can see that the VMS deposits are clustered in areas such as Rouyn-Noranda or Matagami. We wanted to see, but in the modern, as you can see on the left-hand side, that the modern equivalents of VMS, SMS, are found along rifts. So is there any indication, or is there any preservation of some of these rifts, not necessarily linear rifts, but broad areas that could have been rifts in the past that were then subsequently deformed at later stages? This just shows that the VMS deposits are not equally distributed temporally as well. So on the bottom plot on the left here, you can see that the majority of VMS deposits are Deloro or Blake River, with some of the lower occurrences in the other assemblages. So key thing is, how do we connect these deposits on a sub-province scale? One of the key drivers of this study was the work done by Chris Galley on the gravity inversions that he showed you in previous Metal Earth meetings and also yesterday. And Chris was able to isolate the density isosurface that corresponds to the Moho boundary. And this is the surface shown here on the right-hand side. You can see that he's identified these shallow Moho anomalies outlined by the thin white lines. So these are clear linear zones or linear zones of shallow Moho. And when you actually look at them and compare the location of VMS deposits, around 75% of the VMS deposits lie within these shallow Moho anomalies. So is there a relationship between the location of the VMS deposits and these scars of rifts, or these potential preserved rift structures? So Erin took this work and she wanted to kind of test this idea of if we can see any evidence for these rifts at surface. So what is the evidence of this rifting at surface? If they are preserved, then there should be some evidence of let's say rift markers, that even despite the deformation, you should have some evidence that remains. So these are the rift markers that Erin compiled. So these again are sub-province databases and sub-province data sets. So looking at that scale, not down at the individual assemblages, but on a sub-province scale. So she collected crustal scale faults across the entire sub-province. Then she also looked into the mineralization and alteration across the sub-province. And then she also wanted to look at key lithologies. If you take this cartoon at the bottom here, you can see that you might find more komatiites in the center of an Archean rift. You might find banded iron formations to the more distal areas of the rift, and maybe ultramafic intrusions towards the center of the rift as well. So these comparisons would provide a first-order test to see if there's any relationship between the shallow Moho anomalies from the gravity inversions and the structures and lithologies preserved at surface. So this is the first compilation of data. So these are major structures. You can see that the major structures broadly align with the shallow moho anomalies. Some of the major structures, such as the Casa Berardi and the Cadillac Ladder Lake Deformation Zone, are on the edges of the shallow moho anomalies, whereas you have others, such as the Porcupine Dester Deformation Zone, are sitting within or above the shallow moho anomalies. So some of these structures could potentially be in early extensional faults that were later reactivated during later deformation. Here's just a compilation, again, on the sub-province scale of mineral occurrences. I just have two examples from Erin's work. This is zinc. You can see that there are some, this is the density of occurrences, and this is everything from showings to mined deposits. Here we can see that there is a broad correlation, but there's lots of areas outside of this that don't correspond to the shallow moho anomalies. But if we go to the copper occurrences and the densities of those, all of the denser areas of copper occurrences occur within those shallow moho anomalies, which are marked here by the black thin line. Here again is a sub-province scale data set on alteration. Erin wanted to look to see if there was a way of seeing if there was higher alteration values above these shallow moho anomalies. So she used loss on ignition as a proxy for alteration, which reflects hydration and calcitization of mafic minerals. And high alteration zones correlate with the shallow moho anomalies. But again, this data set is not complete. There are lots of areas where we don't have data, but in areas that we do have data, we do see slightly more alteration. And she also acknowledges the fact that clearly there is metamorphism that can affect the LOI, but it's as a kind of a broad proxy on the sub-province scale. Here's another data set she put together. This is surficial sediment geochemistry. So this is arsenic, just as an example. You can see here that there's a good correlation, especially around Roy Noranda, of higher arsenic values in here. And then as you transition across that boundary of the shallow moho, there are lots of data in here, but there's a lot less arsenic values, there's a lot less higher arsenic values in that area compared to Roy Noranda. Again, broad correlations, but again, we're working on the sub-province scale. In terms of the key lithologies, so just note that these polygon sizes are enlarged for visualization purposes, and they enclose lithology. So they're not representing individual flows, let's say, of the komatiites, but kind of just to show you their location. Just to point out a few things in terms of the locations of the key lithologies with respect to the shallow moho anomalies. You can see in the north, for example, you've got mafic, ultramafic intrusives. They sit in these areas such as the shallow moho anomalies underneath Shibugu and Matagami. This could be related to deeper erosion in the northern volcanic zone, whereas in the southern volcanic zone you see that there's a lot more komatiites in the centers of these shallow moho anomalies. And as we mentioned before, the banded iron formations should be potentially on the edges of these rifts, or of these, and that's what we see. So above Timmins and Matheson, you can see that there are lots of banded iron formations to the north of that anomaly, and just south of Matagami, you can see that there are large bands of banded iron formations, which could indicate that they are forming distally to what would be the center of the rift, at the center of these shallow moho anomalies. So the collated data of rift markers when compared to the shallow moho anomalies show that there's a broad correlation, more in some data sets than in the other, between the rocks at surface, and even despite any post-volcanic deformation or translation that has occurred. So this potentially supports the hypothesis that these rifts are in fact preserved or partially preserved. So based on the correlations with the surface geology and the shallow moho anomalies, these rifts may have been active in the Archean and partially preserved. So what about the rift architecture? If we assume that these shallow moho anomalies were rifts, then we can start to connect them and start to build this rift architecture and evolution. So we're not only talking about what their interconnectedness is, but also their timing. So you can see in the top here, you've got this major rift system in the north that we could potentially link Chibougamau and Matagami. And then in the south, we see that there's another one linking Timmins and Matheson and Roy Noranda. And then we have this oblique anomaly here, which connects them. So some of the questions that Erin wanted to answer from this was, how do these evolve over time? And are there any modern analogs with similar rifting styles that we could potentially learn from? So we just have a couple of examples. We always go to the Lau Basin as it's our go-to place. So this is the first place to look at. This, on the plot on the right, you can see the crustal thickness model from Chris's work that was published last year in JGR. You can see that the rifting in the Lau Basin is quite different in the north here versus the south here. So we have multiple parallel spreading centers and rifts forming in the north, and these are connected by these transcurrent faults. But in the south, you can see that there is only one single rift. What's also notable as well is that the crustal thickness in this area is a lot thinner than we have in the Abitibi. So there are some similarities, but some differences as well. Here's just another example of an area that has a rifting with thicker crusts. So this is the Yamato Basin, just in the northwest of Japan, in the Japan Sea. You can see there's seismic velocity profiles just showing the thickness and variation in the Moho topography. And if we take a quick look between the Moho topography from Chris's paper on the left and the one from Sato et al. On the right, you can see that the wavelengths of the variations are similar in some instances, but not the depth or not the thickness changes that you see in the Moho. So again, some similarities, but some differences as well. The third area that Erin was quite interested in looking at was Iceland in terms of a rift architecture, particularly because of a couple of features that are similar to what we expect in the Archean. So the first one would be the crustal thickness. Here we have crustal thickness of up to 40 kilometers. And the second would be the elevated mantle temperatures that are related to the Iceland plume, which is represented here by this yellow circle. You can see that the rift architecture in Iceland is actually quite complicated. It probably, I don't know if many people are familiar with the tectonics of Iceland, but you have the eastern rift zone and the northern rift zone, which are the active rifts. These are rifting and also propagating to the north and south. So this is the active rift zone. You've also got a dying rift zone, the west rift zone over here. Where you've had a rift jump, essentially. And then you've also got these oblique interconnected rifts, so the central rift zone and the South Island seismic zone, which are connecting these two rifts. So the rift architecture here is quite complicated, and you're even forming small microplates in between these areas. So Erin made this really cool diagram, which I love. So we've now taken Iceland and flipped it, just so we can get the same orientation of the Abitibi. On the left-hand side, you can see the color scale represents age of rock. This runs from this goes from 15 million years million years ago in the purple, all the way to 0 present day in the orange colors. On the right-hand side, we've got the same color scheme. But we have 50 million years of the volcanic succession in the Abitibi. And you can kind of see there are some similarities in this area where we have two different rift zones and where we have older rifts potentially in the northern volcanic zone, and then you may have had a rift jump, and then there are interconnected structures oblique to this, which may have accommodated that rift jump. So again, some interesting places to explore further. In terms of the rift architecture, rather than necessarily the rift, what's driving it, let's say. So just as a summary, so gravity inversion modeling identified shallow Moho anomalies that correspond to the location of the VMS deposits in the Abitibi greenstone belt. You saw that over three quarter of those sit within these shallow Moho anomalies. And if these shallow moho anomalies are related to rifting, then the evidence for rifts should be in the shallow crust. So Erin put together these databases on the subprovince scale, such as crustal scale faults, rift lithologies, and alteration, and they do overlap broadly in areas where we have data. And even despite significant upper crustal deformation, we still see that there is this apparent connection between the moho, the shallowing of the moho, and the rift markers. Examples of modern rifting areas show some similarities to the features, particularly in Iceland, for the reasons I outlined: thicker crust, let's say, higher heat flow. But more work is needed to explore how these rifts form and how they may be used to identify new exploration areas for VMS deposits. The interesting thing is that if there is this connection between the shallow moho anomalies and rifting, then maybe in areas where we don't have VMS deposits, but we do have shallow crust, they may be places that we could potentially look for new VMS deposits. So I'll leave it there, and happy to take any questions or pass on any comments to Erin.